Hello, everyone, and good day. I hope you enjoyed that cool video. It's a really interesting reaction. A reaction between ammonia, which typically is in solution, so it's ammonium hydroxide, and copper chloride. And we're going to be talking about that reaction. Now, hopefully, based on what you observed, you have noticed that it's a double replacement reaction. So, question is, how can we predict if a double replacement reaction is going to be spontaneous? Right. And we heard a new word, and that new word is precipitation. So double replacement reactions are also called precipitation reactions. And hopefully you remember precipitation like rain as in coming down. In chemistry, precipitation is a little bit different. It's not just the forming of water. It's actually the forming of a solid. Precipitation by definition is a substance that changes or goes from being dissolved to being undissolved. So you have to be dissolved to become a precipitate. If you're not dissolved in the first place, like if you just drop a rock in water, that's not considered precipitation. That's just boop, a rock. Okay. And why is that so special? Well, what I wanted to show you is what happens when you dissolve any ionic compound. We know that a solid ionic compound looks like this, right? Well, when you dissolve it in water, it actually changes. So if this is my water, what happens is that that crystal structure breaks up and the bonds kind of start floating everywhere. Now, it's very hard to see them floating because obviously this is a two-dimensional picture, right? But I have a cool little simulator that actually should help us. So I'm going to stop sharing that, and I am going to share something else. I'm going to share one of these. So we're going to look at assault, not assault like, the beating up of people. That's just wrong. We're going to look at salts because all ionic compounds, by definition, are salts, and all salts are, well, ions made up of ions when dissolved in water. That's what makes a salt. Okay. So just a little vocab. When you dissolve the salt, we call it turning the salt into free mobile ions. Now, this is super confusing in that when you dissolve the salt, you are not actually chemically breaking it up. I know it might seem like you're chemically breaking bonds, but you're not. And the reason you're not is because if you were to evaporate all that salt, all of the crystallized structure would reform together. It's a little bit different. That's as far as you need to go in it. Okay, but what I wanted to show you is what we mean by these free mobile ions, because in real life uh, things don't work as perfectly. So it's gonna be super slow. I apologize. And what I wanted to show you all is you see these nice little, these are two little cubes of salt. The red ones are going to be the sodium, the green ones are going to be the chloride, and they're in two cubes. You kind of have one in front of the other, that they're in that nice picture right now. I'm sorry, that nice lattice structure. Once we put them in the water, the second they hit the water, they dissolve. And by dissolve, I mean that they start to float around, and they always continually float. So this is what I mean when I say free mobile ions. Notice how the ions are moving around. They're free, they're mobile, they have the ability to move, right? So free mobile ions, okay? Okay, so back to our notes. And I'll write that down for you. So we said that there are free and mobile ions. Okay, so let's specifically talk about double replacement reactions. And the reason that I brought all of this up is that for a double replacement reaction to be spontaneous, you must have one product that is soluble and one product that is insoluble. And how do we tell solubility? Well, we actually have a reference table, table F. Here is our solubility guide. And you kind of have these two different sections over here, and these are the keys here. Over here, this is for things that soluble. So what this first column cell is saying is that anything that bonds with a group 1 ion, any anion that bonds with a group 1 cation is going to be soluble. Any anion, right? Same thing with ammonia, same thing with nitrate. But down here, we see that for halides, when cations bond with halides, not all of them form soluble compounds because there are exceptions to what is soluble. When you combined with any three, either any of these three ions, you form insoluble stuff. Okay? So yes, salts, soluble, insoluble. And then over here on the other side, it is the same but opposite. These form insoluble compounds, except when bonded with this stuff. So carbonate, it says when bonded with group 1 or ammonium, which, by the way, over here, right? So if you have a carbonate that's bonded with group 1 or ammonium, right, it's going to be soluble. Otherwise, carbonates are insoluble. So that's how we can tell. Now, not only must we have a one of our products to be soluble and one to be insoluble, but also both reactants must be soluble. And the reason that both reactants must be soluble is we need the water. We need to be able to be underwater for these to actually chemically react. Need to be in that free mobile ion form to chemically react. So both of our reactants must be soluble. Only one of them can be insoluble. And I want to talk about why our products, why we have to have only one insoluble product. let's say we have two quote unquote, I'm sorry, two soluble quote unquote products, right? Or let's say instead of we create. So let's look at a reaction. We'll have a blue purple plus a red green. And by the way, when they're soluble, we do give it a little subscript of AQ, yielding, if this was a double replacement reaction, we would have blue, green, then we would have red plus red, purple. How do we know which comes which? Well, if these are both ionic compounds, we know that in the chemical formula, the first one's a positive and the second one's a negative, positive, negative. And we see that if there's going to be a switch, we can't have the green and the purple bonding together because those are both negative. We can't have the blue and the red bonding together, both positive. So that's how I got that. Okay. So when we dissolve, when we dissolve these products, so we're going to take these products, we're going to dissolve them in water. What it's going to look like, we're going to have a bunch of green. All right, I want to write that these are both soluble. We're going to have a bunch of purple. Have a bunch of red. And we're going to have a bunch of blue. Now, there should all be 1-to-1. I didn't count properly, so I apologize for that. But the point I'm trying to make is we see that if both of our products are soluble, there's no real new bonds. No new bonds are created. Let's look at a situation in which there is a spontaneous reaction where one is insoluble and one is soluble, and what would happen. So we're going to take hold on. Sorry. Wow. Not doing too well. There we go. So instead, what we're going to say is that the red purple is a precipitate, which means that it's going to be solid. When I react these two, when I dissolve those two, we start with, and this is the instant that they dissolve. 1, 2, 1, 2, 1, 2, purple, 1, 2, 1, 2, green, 1, 2, 1, 2, red, 1, 2, 1, 2. So that's before a reaction happens. Now let's look to see what happens. after the reaction. So what we're saying is that there is a red purple that is at the bottom here. It's basically, if you form something insoluble, it floats to the bottom, right? So we're going to have this red purple. Right? Salt. And then we're also going to have blue and green ions floating around. 1, 2, 1, 2, 1, 2, 1, 2. And we can see here that in the situation in which we made a solid, we can clearly tell that this red purple actually did form, right? That's in that nice long structure. So we know that if we were to remove this salt and all the water, the only thing left over would be the blue green, which is very different than if they're both soluble, in which we have no idea if anything's even forming. And as it turns out, if these are both soluble in the beginning and these are both soluble at the end, really it's going to be, when we dissolve the water, it's most likely going to go back to this one over here. It's most likely just going to form random salts if you remove all the water. Okay, let's do some practice, because that's where the challenge is here, on how to tell if a reaction is spontaneous or not. We can start with LiCrO4 lithium chromate plus iron 2 acetate. Oops, sorry. C2H3O2. And that's a double replacement. So why did I make this so far away? Oh, that's why. I'm going to make it a little bit far, not that far. That's better. And that's going to do a little flip-flop. So we have LiC2H3O2 plus FeCrO4 2. First thing I'm going to do is balance. I need to throw a 2 over here. And I need a 2 over here. And I'm all balanced. Next thing I'm going to do is I'm going to double check my table F. And based on table F, lithium chromate. Well, lithium's a group 1. So anything with the lithium bonded to it is going to be soluble. Soluble, remember, is AQ. AQ. Here's another lithium. So that's AQ. Okay. And then we have iron acetate and iron chromate. Let's take a look. Let's see. Acetate. Oh, I found acetate right here. It's all soluble. And chromate, chromate's insoluble, except when combined with group 1s. Okay, so acetate, always soluble. Chromate, insoluble. This would be spontaneous. Right? Okay, one more. We're going to do, and this is a pretty famous one, AgNO3 silver nitrate plus NaCl, our friend sodium chloride. Double replacement, we can do a flip-flop. Ag is +1 and NO3 is -1. Na is +1, NaCl is -1. So we would get AgCl plus NaNO3. Now, the good news is that because we're using a group 1, always soluble, but in case you forget, look at that. Group 1s are soluble. Oh, and so are nitrates, right? So anything with NO3 in it or a group 1 is soluble. So let's fill those out. AQ, 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 all right? So now we have to find silver chloride. Let's see. I don't see a silver, but I do see halides down here, which say they're always soluble, except when bonded with silver and or lead or mercury, dimercury, right? So that's actually going to be insoluble. And that would make this a non-spontaneous reaction. Okay? And that is how we do double replacement reactions. Thank you so much for watching today. Bye.